Hello, everyone, and welcome to the fourth installment of Thorlabs Microscopy webinar series, How to Build a Microscope. Our talk today is about laser scanning techniques and applications, the fundamentals of multiphoton and confocal implementations of laser scanning microscopy. I'm Sergey Matveev, your moderator for today and application specialist at Thorlabs Imaging System Division, where we develop microscopy systems for life sciences. I'm happy to introduce our speaker, Henry Haeberle, who is an application specialist at Thorlabs. He is a neuroscientist by training and subsequently worked in imaging core facilities. At Thorlabs, Henry helps customers find solutions to their imaging needs and supports any technical inquiries that may come up during everyday use of their system. One last thing before I hand it over to Henry. Please feel free to submit your questions throughout the presentation, and we will try to get to them all at the end. The QA button can be found at the top right of your screens. And now, it is my pleasure to yield the floor to Henry.
Thank you so much, Sergey. So today we are talking about laser scanning techniques with a particular focus on confocal and multiphoton. This is the fourth talk in our webinar microscopy series, and we'll build upon the concepts described in the first three talks. So those talks can be found on thorlabs.com/webinar if you'd like to go back and review them after this talk. There are two further talks in this series that will build upon the concepts described thus far. The next talk will be on advanced imaging techniques, where the Thorlabs Imaging Systems Division is going to describe some of the new technology development in this area. So in today's talk, I'm going to focus first on the fundamentals of laser scan imaging, and then I'm going to talk about the mechanism that allows us to achieve laser scanning, which is the scan engine. First, I'll talk about the trade-offs in scan engine design, and then briefly talk about four key elements of the scan engine: the scan lens, the tube lens, scanners, and detectors, and the key specs involved in each. Next, I'll talk about confocal specific scan engine design, including going through a brief overview of confocal fundamentals, and then followed up by showing how the confocal fundamentals affect confocal scan engine design. Finally, I will finish with multiphoton specific scan engine design, again with a brief review of multiphoton fundamentals, and then talking about how those fundamentals affect multiphoton microscope design. So first, so far in this series, we've been talking about wide field imaging, and that involves flood illumination of the entire field of view at the same time, and then capturing an image from all the areas of the field of view at the same time with a camera that can have a large area. This is fundamentally different from point scanning, where one is using lasers to illuminate only a single point at any given time. In order to generate an image in wide field, since one is illuminating the entire area at the same time, you could use a camera to capture with different pixels spaced over the image space to simultaneously image the whole area. With laser scanning, the excitation laser spot needs to be rastered across the field of view, and then the image can be reconstituted after rastering across the entire field of view. So this rasterization typically uses two scanners: a fast scanner, which can move the laser quickly along the, in this case, x-axis lines, and a slow Y scanner that can then advance line by line to the next line. Now, because the scanners have acceleration limitations, there is a turnaround for the fast scanner on either side of the image. And once the image is complete in the bottom right-hand corner, there is a flyback where both the fast and slow scanners reset back up to the beginning of the image for the next frame. So why do we use laser scanning? It's not because it's intrinsically superior to wide field imaging. In fact, you could consider it to be intrinsically inferior to wide field imaging. That is because you're only illuminating one point at any given time, so it would take longer to raster across the whole field of view than simultaneously imaging the whole field of view as you would with wide field imaging. No, instead, laser scanning is superior because it provides a foundation on which one can build higher level technologies. Today, I will be talking about two of those technologies, confocal imaging and multiphoton imaging. So confocal allows one to section the tissue, that is to exclude out of focus light. So in this example of the same convallaria slide, on the left you see wide field imaging, but because the slide is thick, you see some blur to the image, whereas confocal imaging excludes that out of focus light and you get a crisp image. Now, multiphoton imaging grants one the ability to image much deeper into biological specimens and tissue than you can with either confocal or wide field imaging. So let's talk about the scan engine, which is the design under which one can achieve laser scanning. There are four key elements to a scan engine: the scanner, the scan lens, the tube lens, and the objective. Now, these need to be laid out in a very specific manner. So all of the optics in a scan engine are compound optics, but they can be represented as having an effective focal length. So the design of the scan engine requires placement of these optics in particular locations. So working from the left to the right, the scanner should be located at the effective focal length distance from the scan lens. That is the back focal length of the scan lens. And the scan lens and the tube lens should be placed at the right distance apart, that it's the sum of the front focal length of the scan lens and the back focal length of the tube lens. Now, the tube lens and the objective spacing is not quite as, doesn't have quite the level of requirements, because here the laser beam is in so-called infinity space and it's collimated. However, it's still good to line up these two optics such that the front focal length of the tube lens matches up with the back focal length of the objective, or the back focal plane of the objective. Now, before we go further, I'd like to review how magnification works in 4F's microscope systems. This was covered in part 1 of our series, How to Build a Microscope. To just summarize here, image magnification in a microscope is achieved by a combination of the objective and the tube lens. And the magnification of the object to the image plane is a ratio of the tube lens effective focal length divided by the objective effective focal length. So in this case, the tube lens is 180 millimeter effective focal length. The objective has a 3 millimeter effective focal length, and therefore the magnification is 3 times. This magnification also applies to scan engines. But in this case, it's at the intermediate image plane, which exists between the scan lens and the tube lens. This magnification, though, is still dependent on the same ratio. It's the ratio of the tube lens effective focal length to the objective effective focal length. Now, one other piece of review I'd like to cover is field of view. So the field of view for an objective is the effective focal length of the objective and times the tangent of the max acceptance angle that the objective can relay to a focal point in the image. That is the most off-axis angle that can be accepted by the objective and relayed to a focal point in the image. So I bring this up because field of view in a scan engine is often limited by the scan engine optics, not the objective. So in a scan engine, the maximum angle that the light coming out of the scanner is relayed is reduced by the scan engine magnification before it goes into the objective. That is, if omega 2 here is the angle of light going into the objective, and omega 1 is the angle of light reflecting off of the scanners, omega 2 is omega 1 times the scan lens effective focal length divided by the tube lens effective focal length. So essentially, these angles are reduced by the scan engine magnification. So this limits field of view in two ways. One is the scanners in your system will have a max off-axis angle. And because rasterization will usually use two different scanners, this will generate a square. Now, the scan lens itself has a limited field number or area of field of view. And since that's radially symmetric, that will limit the imaging area as by a circle. So if we're looking at an image, you can imagine the objective field of view would be this red circle here, and your actual field of view of your scan engine is going to be further limited by the scan lens field of view or field number, which is in blue here, and by the maximum angles of each scanner that's in the scan engine, indicated by this purple square here. So you may think that if this angle is reduced by the scan engine magnification, then you would want a scan lens and tube lens to have a 1 magnification, so this angle is not reduced. But there are other trade-offs in scan engine design that we're going to want to be thinking about. And one of those is the maximum beam size you can place into an objective. So the largest area of beam that can reflect off the scanner is limited by the clear aperture size of scanners. This will then be magnified by the scan engine, which is the same ratio of tube lens and scan lens effective focal length that I've showed you before. So therefore, the max beam size that can go into an objective is the scanner clear aperture diameter times the scan engine magnification. This is important because fulfilling the diffraction limited resolution of the numerical aperture of the objective requires a perfect top hat illumination of the back aperture. That is, the back aperture of the objective needs to be fully illuminated with even illumination to achieve maximum resolution. Now, real lasers have a Gaussian distribution of their beam. So with the more energy in the middle of the objective than near the edge, you get a slightly reduced resolution and a larger illumination spot. Now, if your scan engine limits the size of the beam that can be achieved, you may underfill the objective even further, reducing your resolution even further. Now, so far, this has very nicely demonstrated in the classic paper by Helmchen and Denk, where they showed the normalized focal spot size on the y-axis here compared to the diameter of the excitation beam into the objective as a ratio to the back aperture diameter. So to achieve a 1 focal spot size or ideal resolution, you need to overfill the back aperture of the objective. And then as you reduce the beam size, you reduce your resolution in both X and Y and Z. And the key thing to keep in mind here is that the Z resolution decreases even further than the XY. So you're losing much more Z resolution than XY as you underfill the objective. Now, so far we've been talking about ideal samples where all the light rays follow a ballistic straight line pattern. But real tissue is going to cause scattering and wavefront aberrations that are going to mess up the point of focus. And this can be NA dependent. So in tissue that has a lot of variance in its index of refraction, these high numerical aperture rays coming in from the angle might actually cause destructive interference at the point of focus and mess up the wavefront, increasing the focal spot size. Whereas maybe an underfilled objective, that does not have these high NA rays, and then you get a better shaped wavefront, and so you get a tighter focal spot size. This was reviewed in the previous talk in this series on multiphoton microscopy on how to select the right ultrafast laser. And for multiphoton imaging, I highly recommend you go back and review that talk. So here they describe this effect from a paper by Don Wallace, Colonel Burns, and Tromberg. And they demonstrate here that the numerical aperture of the for excitation NA has limits when imaging deep. So on the y-axis of this graph here is detected autofluorescence, which you can think of as a proxy for focal spot size. The smaller the spot size in multiphoton imaging, the brighter the fluorescence. So you can see here at shallow depths, as you increase the numerical aperture of the objective, this fluorescence keeps increasing, showing you that your focal spot size is decreasing. Now, as you image deeper into tissue, you can see the higher NA objectives, it starts actually hurting you rather than helping your resolution. And it looks like that the optimum NA for imaging deeper into tissue is closer to 0.6. So therefore, you have a resolution versus depth of imaging trade-off. If you overfill the objective, you are going to achieve the full resolution of that objective near the surface of the tissue, and you'll get your best resolution. However, because of the scattering and other wavefront errors introduced by the tissue, you will not be able to image very deep. On the other hand, underfilling the objective, you can see here the resolution is reduced, but you're able to image much deeper into the tissue. So now I'd just like to cover the Bergamo series of microscopes and how their scan engines are designed. So we've designed a scan engine that has a beam magnification of 4. The resonance scanner's clear aperture for our systems is 5 millimeters for a maximum beam size into objective of 20 millimeters. Now, the Gavo maximum clear aperture is 4 millimeter, and I'll get into why it's smaller later in this talk. So the maximum beam size is 16 millimeters going into the back aperture of the objective. So now I'd like to just briefly talk about the optics that are in the scan engine and why we use specific types of optics in the scan engine. So one cannot use just simple spherical lenses because the focal spot will trace out a semicircle, not a flat line perpendicular to the scan engine axis. So since we generally want to be imaging a flat line in the sample, these spherical lenses will not do. Instead, one can use a flat field scanning lens, which is a compound lens that corrects for this field curvature and allows you to image in a flat line perpendicular to your scan engine axis. However, here, the focal point is a product of the focal length of the scan lens times the tangent of the angle of the scanner. This is problematic for a number of reasons, because what it means is that this is a nonlinear relationship. So if the scanner, for instance, is moving at a constant speed, the focal point will accelerate as you move off axis. This causes a number of problems in laser scanning, and so most laser scanning systems use an F theta corrected scanning lens. In this type of compound lens, the focal point is linearly related to the effective focal length of the scanned lens and the angle of the scanner. Finally, scan lenses or scan engines use compound optical elements that have telecentric lens. Now, the telecentric lens focuses light here perpendicular to the imaging plane. So this is important because when you're setting up a series of compound lens in a series, you need to relay this light efficiently from optic to optic. So in these other lenses, the light is going to escape out of the side of the system, whereas here you'll be relaying the light onto the next compound lens. So In our final talk in this series, in the do-it-yourself microscopy, we'll talk in much more detail about the individual specifications of these compound optics. Here, I'd like to just focus your attention on 4 key specs for scan lens. The first one is focal length, because it will affect the magnification of the scan engine. The second is entrance pupil diameter. This is the max diameter size of a laser beam that a scan lens can accept and focus to a diffraction limited spot. It's important to keep this in mind relative to the size of the scanners. If the scanner is larger, one is wasting some of the clear aperture size of the scanner. And if it's smaller, then you're wasting the capability of the scan lens to accept a certain width laser. The third key element is the field number, or the area on the intermediate image plane that the scan lens can focus to a diffraction limited spot. Finally, your scan lens are going to want to be designed for the wavelength that you're interested in for your experiments. So this will be important both for the diffraction limited performance as well as the transmission efficiency. So now on to tube lenses. So like with scan lens, we're going to want to focus on the focal length of the tube lens so that you get the proper magnification in your scan engine that you're interested in. The second key stat will be the image plane field of view. So this is going to refer to the intermediate image plane between the scan lens and the tube lens. And this is basically the size of this plane. You're going to want your tube lens to be able to be matched, its field of view to be matched with the scan lens field number. Otherwise, you're wasting capabilities of either the scan lens and tube lens if this area does not match. The third key spec is going to be your entrance pupil diameter, which in a scan engine is a little counterintuitive. It's actually referring to the pupil on this side with the objective. So this entrance pupil diameter, you're going to want to have be at least as large as the back aperture of your objective that you plan to be using in your system. Otherwise, you will be underfilling your objective. Finally, just like with the scan lens, you're going to want to be able to select a tube lens that functions in the wavelength range that you're going to be using. All right, so far we've been talking about all the compound optics in a scan engine. So now I'll just briefly run through the scanners themselves. So as discussed before, you'll be using 2 scanners, a X resonant fast or X scanner or fast scanner and a slow Y-axis scanner. So the fast scanner will raster quickly each line, and then the slow scanner advances each line and provides the flyback. This is often implemented in a scan head where the laser beam will bounce off one scanner, typically the smaller or fast scanner, and then a second scanner, typically the slow scanner, which is frequently larger. So let's now talk about different scanner types. So there are 2 broadly different types of scanners, galvo scanners and resonant scanners. So galvo scanners give precise control over exact positioning. So one can send an analog signal to the scanner and have it move to a particular angle. The drawbacks to galvo scanners is that they have relatively low acceleration and they have relatively low maximum speed. Furthermore, galvo scanners have a size versus speed trade-off. So as we mentioned before, the clear aperture of the scanner limits the size of beam that travels through your scan engine. Well, you can't just choose very large scanners without having a large speed trade-off. The large galvo scanners will travel slow. So you get around some of this problem by using a resonant scanner. So resonant scanners are fast. 2 frequent speeds that they resonate at is either 8 kilohertz or 12 kilohertz. Now, because they are moving in a resonant movement, they're moving in a sine wave movement with angle versus time. The only control you have over resonant scanners is the amplitude. Furthermore, for resonant scanners, there's a slight speed versus amplitude trade-off in that the 12 kilohertz scanners have a slightly lower amplitude ceiling than the 8 kilohertz scanners. So Scanners are often put together in scan pairs in order to raster an image across the field of view. So your two common scan pairings are GAVO-GAVO and GAVO-resonant scan pairings. So for a GAVO-GAVO scan pair, these, because they're two GAVOs, can target anywhere in the field of view. They can dwell for any amount of time within that field of view, and they can image arbitrary shapes that one is interested in. However, because the fast GAVO is still a GAVO and it has limited velocity and acceleration, if you want to image over large areas, these large areas will scan slowly, a couple frames per second. Now, GAVO resonant scan pairs are significantly different. So because the resonant scanner is fundamentally different than the GAVO scanner, you can only image in a square, rectangle, or line, and you cannot rotate these scanned shapes. Furthermore, that line needs to be along the axis of the resonant scanner, which in this case is the x-axis. So furthermore, because the resonant scanner is resonating around its central point, which is centered in the middle of the field of view, the resonant scanner, the areas of imaging need to be symmetric around this middle line point. However, the advantage you get to resonant scanning systems is that they are fast. Video, frame rate, rate of speed, even across the entire field of view. So a couple of other considerations to keep in mind of GAVO-GAVO scan pairs versus GAVO-resonant scan pairs. So in GAVO-GAVO scan pairs, you have complete control over where and how fast the scanners are going. And so inside the imaging area, you get a constant dwell time on all your pixels have identical dwell time within your imaging area. But because there's a limited acceleration to GAVOs, it takes a while for the GAVO to deaccelerate at the end of a line and then reaccelerate again going in the other direction. This results in an increased dwell time and a fairly large area where the scanner is tracing outside your field of view. So in this image, I bleached a sample on purpose, and this yellow box here represents the area I was imaging. Now, if you look closely, you can see that the bleached area actually extends outward on either side of the box and actually appears to get worse. This is because of the turnarounds on the GAVOs turning around outside of the field of view. Now, a GAVO resonant scan pair has a different set of considerations and issues. So because it's moving in a sine wave pattern, the dwell time is very uneven across the field of view. So this is an example of a 512 by 512 image taken with an 8 kilohertz resonant scanner. The dwell time in the middle of the field of view is about 0.1 microseconds, and you can see the dwell time on the edges is over 2 microseconds, or over 20 times longer. So I attempted to bleach the sample here with a GAVO resonance scan head. And one key thing to keep in mind is you can see because of the pretty short dwell times, the sample is much more resistant to bleaching. However, if you look closely, you'll see two twin dark lines along the edge of the image here and here. That is from the really long dwell times that are occurring at the edge of the resonance scanning scan area. So that means that if you're imaging biological samples, you're going to want to be careful about the amount of power you're depositing on the edges of the sample. And this is one reason why it can be useful to have high-speed power modulation devices, so you can turn off the laser when you're at the edge of the field of view in order to limit the damage to the sample. All right, so before we move on, I'd just like to talk about scanner placement within the scan engine. So we talked before about placing the scanner at the back focal point for the scan lens effective focal length. Now, in a properly aligned scan engine, that will place the scanner close to, if not exactly at, the back focal plane of the objective. This is important because the scanner has a particular shape, and that effective shape will be changing as the scanner scans off angles. We don't want that showing up in your image. So we want the scanner to be conjugate precisely to the back focal plane of the objective. Now, this would be very straightforward to do if our systems were based on only one scanner, but that is not the case. We use two scanners to raster a two-dimensional pattern. And so therefore, the scanners need to be spaced apart from each other enough so that they don't strike each other. So to accomplish this, we space them out on either side of the scan lens focal point so that each scanner is relatively close to the back focal plane of the objective. Now, it will be useful for most imaging requirements, but there are certain applications where it's really important that the scanners get conjugate exactly to the back focal plane of the objective. In that case, one can use a relay lens to relay the light from one scanner onto another scanner, and then both can be conjugate exactly to the back focal plane of the objective. This is typically achieved by using a relay lens in between these two scanners. And these relay lenses are frequently just two scan lenses mounted back to back. So this will provide superior imaging and is sometimes required for advanced imaging techniques. However, it's not always used because for two reasons. One, the relay lens, you're now essentially placing 3 scan lenses in the system, and since scan lenses are one of the most expensive optics in a system, you're dramatically increasing the cost. And the second is you're adding a lot of glass to the system, so you're reducing the throughput efficiency of your excitation lasers, and you're increasing the dispersion when doing multiphoton imaging. So far, we've talked about just 2 scanner systems. However, by adding a third scanner to a resonant gavo-gavo system, you can achieve more interesting imaging shapes. So now we can do high-speed video rate imaging, but with 2 separate areas that one can toggle back and forth. This is achieved because there is now an X-gavo conjugate with the resonant scanner gavo, so that this gavo can toggle back and forth between one and another shape between these 2 images. This is achieved by having 3 scanners, and it's typically done by pairing one set of scanners next to the scan lens and then having a relay lens and placing the other conjugate scanner on the other side of that relay lens. However, one could also use 2 relay lenses to achieve this same system and then perfectly conjugate all those scanners to the back aperture of the objective. All right, one final element of the scan engine before we move on, and that is talking about the specifics of a laser scanning detector. So these requirements are significantly different than cameras that we would use for wide field imaging. And the first requirement is that these detectors need to be very fast. And that's because we're rastering across the field of view. We're often not over any individual pixel in the image for very long, often less than 0.1 microseconds. In addition, we want a large sensor area so we can capture as many photons as possible. So the traditional detector that's used in this type of system would be a PMT. So these have nanosecond rise and fall times, so it's fast enough to satisfy this requirement. They also have high dynamic range and low read noise. But the price you pay for the speed is their quantum efficiency tops out at just over 40%. This is versus cameras where their quantum efficiency, or the ability to translate photons into electrical current, can be 90 to 95% or higher. So because of these limitations, people have been looking at alternatives to PMTs. The first I'll just briefly cover are avalanche photodiodes. These are single-stage amplification devices that do have a much higher quantum efficiency and are fast. However, they have a lower dynamic range and they're very sensitive to too much light, so they can be easily damaged outside of very low light paradigms. So to get around those problems, hybrid detectors have been developed, which combine the design of avalanche photodiodes and PMTs. However, hybrid detectors have some of their own issues to make it difficult to image with. So a third one possible detector that's being worked on is the silicon photomultiplier. These leverage the large development in CCD technology that's come about in the last 5 to 10 years to try to put together a high-speed multi-pixel detector that could be used in this type of setting. All right, so now we've finished talking about the scan engine elements, and I'm going to move on to confocal specific scan engine design. And to start, I'm going to just do an overview of confocal fundamentals. So to review, confocal is a method to reduce out of focus light in your image. So in this example, in wide field imaging, you have an excitation hourglass of light that's centered around the focal point. Now, if the sample is thick and can emit light through the entire thick sample, you can have emitted light coming from out of the focal point that can reach back through the system and into the camera, and that results in image blur. Now, if you can exclude this light by somehow selecting just around the focal point, you can get a much clearer image without that out of focus light, and that's what confocal aims to achieve. And the way it does it is by placing a pinhole in an image plane. So in this case, you have a laser excitation that is exciting your sample with an hourglass around the focal point. Now, areas of the sample that are at the focal plane are going to emit light up through the scan engine, and then this is going to be focused perfectly on the pinhole. It will reach through the pinhole and reach the detector. Now, light that's from out of focus, so for instance, sample light that is excited by the excitation cone beneath the point of focus, is going to be focused above the pinhole. And therefore, this light is going to expand here after the point of focus. And then most of these photons are going to strike the side of the pinhole and not make it through to the detector, getting excluded from the detector. Similarly, light that's excited or emission light that's generated in the top part of the cone of the excitation light that comes from above the point of focus is going to focus behind the pinhole. And again, most of the photons are going to strike the side and are not going to make it through the pinhole to the detector. In this way, confocal microscopy excludes out of focus lights. And this is included in a scan engine by generating another lens next to the scan engine that will generate another image plane. So in this case, you have this dichroic that sends your excitation light down to the sample, and then the sample emits light that goes through your scan engine, reflects off the scanners, and is focused by another lens onto another image plane. This is conjugate to the intermediate image plane inside the scan engine. Now, if you place a pinhole at this image plane and then a detector behind it, you have your confocal scan engine. And the key element to keep in mind here is that as the scanners rotate and the excitation light moves off axis through the scan engine and illuminates a point off axis at the sample, the emission light traces the exact same path, still travels through the dichroic, and still focuses exactly on the pinhole, so that this whole system can work for not only points exactly in the middle of the field of view, but every point that's in the focal plane. This allows you to exclude out of focus light. So now by stepping through a Z-stack and taking images at various points along the Z-stack, you can then reconstruct a 3D image that looks perfectly in focus because we've excluded all the out of focus light and stepped through a 3D structure. So to finish this talk, I'm going to talk about multiphoton specific scan engine design. And to start, we're going to talk about multiphoton fundamentals. So this, again, is a review from a previous talk in this webinar series, Multiphoton Microscopy for Selecting of Ultra-Fast Lasers. Please go back and review that talk. It's a great overview of multiphoton imaging. Just to summarize here, though, I'm going to walk us through Jablonski diagrams for 1 and 2 photon imaging. So depicted here on the right is energy diagrams with a electron in the ground state. In this case, blue high energy photon excites this electron up to the excited state. It then relaxes slightly over a period of time called the fluorescence lifetime before this electron drops back down to the ground state and emits a photon of slightly lower energy. Now, the same process can occur at very high light intensities. Two different photons can sum their energy to a single electron in a fluorophore, exciting that electron up to the excited state. After that, it passes through the same fluorescence pathway and then emits a photon that now has more energy than the excitation energy used to excite the electron. This requires incredibly high photon density to achieve this near simultaneous excitation, near simultaneous two photons striking the fluorophore near the same time. So therefore, we require pulsed lasers with very high peak power, because a continuous wave laser at the intensity levels required would just vaporize your sample. So why are we using this for multiphoton imaging? Why do multiphoton imaging? Well, the primary reason is, at least for biological specimens, Mie scattering is the primary limit to imaging deep into tissue. So the longer the wavelength of excitation light, the deeper into tissue one can image, with a slight exception at certain wavelengths where water absorption decreases the efficiency. So by using two photon, longer wavelength, low energy photons, you can image much deeper into tissue than with single photon. There is a second benefit to multiphoton imaging. It's what I call intrinsic sectioning. So in this classic image taken by Zipfil, Williams, and Webb, they've imaged 1 and 2 photon into a fluorescence beaker. In 1 photon, you see the hourglass excitation of all the fluorophores, both above and below the point of focus. In 2 photon, though, you only see 1 illumination point at the point of focus. And that's because that is the only place where the photon flux density is high enough to achieve 2 photon excitation. This means that there is natural sectioning. There is no out of focus emission light. No pinhole is required. Now, the light from multiphoton is emitted in all different directions. So ideally, to pick up this light, we would like to put detectors in a sphere around the sample to totally collect the light that goes in all the different directions. Now, unfortunately, this is not really practical. So most multiphoton microscopes just collect the light that is collected through the objective. However, for multiphoton scan engine design, we want all of these photons of light. We don't need to descan them or send this emission light back through the system because there's no pinhole. Instead, we're just going to use collection optics and send it directly to a detector. To make this most efficient, we're going to place the dichroic directly behind the objective and then have a series of collection optics that efficiently translate this emitted light directly to the detector. And that is because every photon that comes out of the sample, we know was emitted from the excitation point of focus. Now, in an ideal sample, this is going to result in ballistic ray photons that are traveling in straight lines through the entire system and would be easy to collect and detect. However, we are frequently using multiphoton on real samples that have scattering, and therefore the angle of the light rays might come in at off angles. Now, every single one of these photons we know was emitted from the point of focus, and therefore every one of them is carrying information about our image that we want to capture. So we're going to want to capture even these off-axis light or photons. So in order to do that, we're going to quantify the off-axis light that comes out of an objective. So this will be quantified in 2 ways. One is the actual size of the back aperture of the objective, and the other one is the accepted collection angle. This together specifies how much of the light from the objective is captured. Now, a fixed certain set of collection optics will be able to collect a larger accepted angle if the back aperture is smaller, and a smaller accepted collection angle if the back aperture is larger. So as I mentioned before, multiphoton imaging allows you to image very deep into tissues. So this is an example imaging 1.2 millimeters deep into brain. And this is significantly deeper than what you could achieve through wide field or confocal, where at most you'd be able to make detail out about 100 microns down into the brain, and maybe at most with confocal 300 microns. So by using multiphoton imaging, you can image several times deeper. So with that, I am going to finish up this microscopy talk. Stay tuned for the advanced imaging techniques talk that is going to be coming out in September. And once again, just to review, previous talks in this webinar series are available at thorlabs.com/webinars. And with that, I would be happy to answer any questions you might have.
Thank you, Henry, for the great talk. I'm going to ask questions that people posted. And we'll go of the very big one first. So can I use the same optics to do confocal and multiphoton imaging? What are the differences that I need to take into account in the detection of the confocal versus multiphoton signals?
Excellent. That is a great question. So ideally, you are going to customize for multiphoton or confocal. So your excitation optics can be the same, although again, you are frequently using different wavelengths of lasers. So you're going to want to have your optics, they would have to be broadband to be able to handle the shorter wavelengths for confocal and the infrared wavelengths in multiphoton imaging. On the collection side, actually, it's ideal to set up two different types of collection paths. We talked about how the confocal collection needs to be descanned in order to relay the light through the pinhole to the detector. That pathway is inefficient. So for multiphoton imaging, you would be losing a lot of light. So you really want that dichroic sitting directly behind the objective to send all those emitted photons directly to another detector, so that you could have more efficient collection of light for your multiphoton path. So it is possible to use the same path, but it's not ideal.
All right, going to the second one. Can you correct aberrations using the electronics? How does the DAC and digitizer contribute to the processing of the image?
So you can correct some aberrations. So if you have pin cushioning or barrel distortion from your scan engine, you could correct that at the image formation level. But the other aberrations, everybody else can step in and correct me if I'm wrong, but I believe the other aberrations you cannot correct with the computer. And so you're going to want to make sure that your scan engine can, achieve the imaging capabilities necessary on those other aberrations.
Okay, this is a very interesting one. What would be the downside of the resonant pair of scanners?
Okay, so that's highly a resonant scan pair has been done. It sets up a kind of spaghetti-like scan pattern that sets up a series of curves that kind of I guess it looks like if you taking an Etch-a-Sketch and then shake it around, you get a series of circles that that kind of scrawl out scribbles all over the image. It's very fast, but you're not imaging in each individual area of the sample in a set way, right? You don't in the raster scanning techniques I described so far. All of the images or all the pixels are imaged in the same sequence from frame to frame. If you do use two resonant scanners, because it kind of spaghettis around, that is not the case. So it's possible, and some people have done it for high-speed imaging, but I would not say it's frequently used in laser scanning.
Okay, going to the next. How does the dispersion affect the image?
So well, this is very nicely reviewed in the multiphoton laser scanning talk. I believe it was the first talk in our webinar series. To point out, in multiphoton imaging, the lasers are pulsed, and therefore each pulse, being short, has different wavelengths of light. The dispersion of the glass then is going to create group velocity dispersion that is going to separate out those various wavelengths in time and space, which effectively means that your pulse gets broadened as it passes through all the glass in the system. So a broadened pulse is going to have a lower peak intensity, and therefore decrease the efficiency of your excitation in a multiphoton system. Now, this can be corrected using pulse correction device that basically introduces the reverse type of dispersion. Although there are limits to that correction and what it can achieve.
So the next one, I think you very clearly described it, but I guess it will be nice to do it over again. Is there a specific type of PMT that we should use? What is the difference between GASP and multi-alkali?
Right. Yeah, absolutely. So, I mean, in practice, Hamamatsu makes the PMTs that we use in laser scanning, and they have multi-alkali and GASP PMTs. And the GASP PMTs have a higher quantum efficiency, so that 40% quantum efficiency that I quoted in the talk is for GASP PMTs. Now, the peak sensitivity range for GASP PMTs, correct me if I'm wrong, but I think that's somewhere in the kind of greenish, between green and red. But they're also highly sensitive to light, and they can be easily damaged by too much light. Now, multi-alkali PMTs have a lower quantum efficiency, but their peak sensitivity extends farther out into the red. So if you're interested in picking up farther red fluors, then multi-alkali PMTs can be superior. In addition, multi-alkali PMTs are not nearly as damage prone. So they can withstand higher light intensities without damage. And so they typically have longer lifetimes as well.
Okay. So follow up on PMTs. What about transimpedance amplifiers?
You mean what is the function of it?
I'll continue reading. I heard we need to use them with PMTs, but I don't understand why.
Okay. Well, because the PMTs output a current, and so most digitizers are going to be looking at voltage swings, and the current coming out of PMTs is going to be incredibly small. So in order to avoid electronic noise, you put a transimpedance amplifier right next to the PMT to take that very small current coming out of the PMT and turn it into large voltage swings. That will essentially boost the signal above the electronic noise in the system, effectively reducing your electronic noise.
We have time for a few more. What is difference between wide field microscopy and confocal microscopy? Are fluorescence microscopy and bright field microscopy also wide field microscopy?
Okay. There are multiple elements to that question. So fluorescence microscopy is basically just talking about the fluorescent mechanism, a fluorophore getting excited by a photon and emitting a photon. So that process underlies both wide field, confocal, and multiphoton microscopy. So I mean, we covered some of the differences between wide field and confocal in the talk. Essentially, confocal is laser scanning that uses a pinhole to exclude out of focus light, whereas wide field will use a traditional microscope with a camera. What was the last part of the question?
Okay, are fluorescence microscopy and bright field microscopy are also wide field microscopies?
So fluorescence, no, we talked about that could be any fluorescence underlies wide field, confocal, and multiphoton. So transmitted light microscopy is typically is typically used with wide field, although I'm sure there's some exceptions out there, but transmitted light microscopy is typically used in wide field imaging.
Okay. Now, then the next question is practically how to exactly conjugate objective focal plane with detection pinhole.
Right. You mean how to place the pinhole so that it lines up right with the image plane, so that it's in a conjugate plane to the image plane?
I assume so.
So I've never done this myself directly, but I would imagine if you could check whether, well, one, it's going to be at the focal point for that pinhole lens, right? So, because right, the light will be in infinity space between the scan lens and the pinhole lens, and then they will focus. The pinhole lens will then focus that light. So you're going to be looking at the front focal distance of that pinhole lens is where the pinhole should be, and then you could check it by, if you just center the scanners and illuminate the sample itself, and then trace like a fluorescent sample, and then watch the light coming back out. You could like use a card, laser safety card or something, to trace the emitted light after the pinhole lens and see where it focuses, and then make sure the pinhole is right there.
Okay. Now, the follow-up on pinholes is optical sectioning depends on excitation pinhole size, right?
Emission. So
this one, there are a few about excitation emissions. So there's a two-part questions. Is it necessary to have two pinholes in confocal microscopy, or just one pinhole in front of detector is enough?
You're referring to that pinhole that was in that diagram. Yeah, so on the excitation side, you just need the laser to be collimated going through your scan engine. So however you achieve that, with a pinhole or not, it will work. The pinhole that most people are referring to when they're talking about confocal microscopy is on the emission side. So yeah, you could build a confocal just with the emission pinhole.
Okay. Then going back to lasers, you said that fast high peak power lasers are needed for confocal. What are the pulse width and energies needed in the lasers that are used?
Those pulse lasers are needed for multiphoton. I'm sorry if I spoke wrong during the talk. So yeah, multiphoton imaging needs pulsed lasers in order to achieve the high energy, peak energy needed for multiphoton imaging.
Okay, and the last question, I think, will be very nice to wrap everything up. Are all the components of laser scanning systems available on the market? Is it feasible to build one on your own?
Absolutely. So that's what we do here at Thorlabs. So if you go to our website, you will see there is a scan engine section where you could just type in tube lenses, scan lenses, and you will be able to find optics that are designed for scan engines for various different wavelengths. So it's all on the website. We have all of those optics that you need. And scanners too.
Okay, we've got actually another one just about now. How effective it will be to use LED light sources in tissue autofluorescence studies?
Well, you would typically use LEDs as an excitation for wide field imaging, and that will work for autofluorescence and wide field imaging.
Okay, I think we are done with all the posted questions. And I would like to thank you, Henry, again for the wonderful presentation and your answers. And I would also like to thank everyone else who attended the webinar today.